Okay, so thank you very much for this invitation and for this opportunity. So what
Giacomo,
I'm gonna,
Giacomo, can
yes,
you take off the mask, or is it, I mean, you're sitting not alone?
yeah, I'm at the moment I'm alone, but I just had COVID, so in case my office mate comes, it's better if
Okay,
I
okay.
keep it. If you can hear me.
Yeah, we can hear you. Don't
Okay,
worry.
sorry. What I will talk about is a few aspects of thermal field theory in the early universe from the perspective of somebody who wouldn't call himself a cosmologist. I come from QCD and heavy ion physics, and I've been applying thermal field theory to the early universe as well. So in particular, what I will concentrate are a few rates that characterize the long thermal history of the early universe, where we had, for instance, many phenomena that were either entering or leaving equilibriums, for instance, dark matter candidates that are freezing out, as they say, so leaving thermal equilibrium, or other mechanisms for production of dark matter or other relics, which instead are called freeze in, meaning that they never reach thermal equilibrium. I would talk briefly about also mechanisms for baryogenesis, and all that quantitatively is governed by rates that compete with what is essentially the standard clock of the early universe, which is the Hubble rate itself, the expansion rate of the early universe. So I will then start first from that, from the Hubble rate itself, and that means from the thermodynamics of the early universe, and touch a bit also phase transitions. And then I will move towards interaction and equilibration rates, first on a more generic, a few generic aspects, and then I will show a couple of examples for interaction rates for massless states and for massive states. So let me then start from the thermodynamics. So the Hubble rate is essentially proportional to the square root of the energy density of the early universe over the Planck mass, well, of the universe in general. Even today, it's proportional to the energy density, but in the early universe, the energy density was, of course, dominated by radiation, which in cosmology means every degree of freedom, which is light. And so here on the right, I'm showing this plot, which plots the result of Leine and Meyer, but it comes from this review, which I will also point to a bit later. So this is the pressure for a standard model early universe, normalized by the pressure of a single non-interacting light bosonic degree of freedom. So you see that at TeV temperatures, the pressure normalized by the temperature to the 40 is rather flat and corresponds to approximately 100 bosonic non-interacting degrees of freedom. And then you start to see that things happen. So as you first cross the Electroweak scale, there is what is called the Electroweak transition, which is, as I will show, it's not really a phase transition for the standard model. And you lose the heavy Electroweak scale degrees of freedom. Then later on, you lose also the bottom and the charm degrees of freedom. Then there's the QCD transition, and later on, you even lose electrons and positrons. So even just in the standard model, there's lots of transitions, even though in the standard model, none of them is strictly a phase transition. And so I will talk briefly about how you compute the thermodynamics across, in particular, across the Electroweak transition. And I will motivate that also in the context of baryogenesis and of gravitational waves, to put it also in a broader context. So baryogenesis, any explanation of baryogenesis, of course, has to satisfy Sakharov's condition, which are these famous three conditions. And Electroweak baryogenesis denotes the attempt to explain baryogenesis with Electroweak physics. So for B violation, then you would rely on the fact that in the standard model, even though Feynman rules and perturbation theory will always conserve baryon number. You have non-perturbative Sphaleron processes that violate baryon and lepton number while conserving their difference. And the state of the art for what concerns Sphaleron is this recent determination of the Sphaleron rate in the standard model at the physical Higgs mass, which shows that at high temperature above the electroweak transition, it's really a rather flat power law in the temperature, and then it becomes exponentially suppressed so that at a temperature of the order of 130 MeV, it would cross the Hubble rate and these processes would become slow. They would so-called freeze out in the history of the early universe. So whatever you want to do, it has to happen around this temperature. So then you would have a mechanism for B violation. You would also have the CKM phases of the standard model for C and CP violation. And if you want to deviate from thermal equilibrium, what you would need is a strong first order phase transition. Because if you have a phase transition, that would mean that in terms of the potential of the Higgs field, it would mean that above a certain temperature, the symmetry is restored. You're in what is called the symmetric phase. The potential is a minimum at 0. Then at the critical temperature, there's a second degenerate minimum, and below that temperature, the real minimum is in the broken phase. Now, if such a scenario were to be realized, then you would have formation of bubbles of the new phase, the broken phase, within the symmetric phase. And then you would have on one side of the bubble, if in particular, if the phase transition is strong, so that the difference in temperature between the broken and the symmetric phase is large enough so that the Sphaleron rate is suppressed on one side of the bubble and is not suppressed on the other, that would give you the mechanism for the deviation from thermal equilibrium that would make electroweak baryogenesis possible. And I'm sure Francesco also already explained it, but unfortunately I missed most of his talk. But if you have a phase transition, and if you have this bubble dynamics with their expansion, deflagrations, and detonation, you also have naturally gravitational wave signatures, and these would also fall in the region of frequencies and potentially also amplitudes that would make them observable by LISA or other future gravitational wave detection experiments. That is all nice, but unfortunately, what is shown in this cartoon doesn't quite happen for the vanilla standard model, because what happens there is that there is no phase transition, not even a weak phase transition. It's just a crossover. And over the next slides, I will show how in general this is computed. So the fact that there is no phase transition was already discovered in the 90s by this series of papers. It's also true that in the pure standard model, there's probably not enough CP violation. So both issues can be addressed in many BSM models, which you can, for instance, introduce new scalars and have a first order phase transition, and then also potentially other sources of CP violation. So I will not try to review the field here of all that. There are many reviews such as this one. I will more focus on how you compute thermodynamics across the electroweak phase transition, and how the lattice and perturbation theory have an interplay there. So because of that, I will start by thinking about how you describe a weakly coupled plasma. Even if, as I will show, even if you assume your plasma is weakly coupled, you will still need non-perturbative input for the electroweak phase transition. And I will also, in a second, compare this situation with that of QCD. So in a weakly coupled plasma, you can think it of being composed of hard quasi-particles, which have energy and momenta of the order of the temperature. So they would be parametrically the largest contributor to thermodynamics. But these hard particles live on top of a background of bosonic soft modes. So the Bose-Einstein distribution, of course, in the infrared has this Bose-enhanced tail, which means that these bosonic soft modes have large occupation number, and so they can be thought of as being classical field. So for these bosonic modes, their loop expansion is not G squared, but it's G squared NB, which becomes G squared T over omega, where here now I'm calling G all the couplings that are parametrically of the same order for the theory you're considering. So in the standard model at the Electroweak scale, this would be all the gauge couplings, the top Yukawa, and the Higgs self-coupling. So this loop expansion, even if G would be small or even very small, would in any case break down if omega is allowed to become of the same order of the numerator here in this fraction. And since omega is the frequency, it can be at its smallest of the order of the mass if your field has a mass. So this, for instance, for the Higgs field, when its mass, which is of order GV, becomes of order G squared T, then the perturbative expansion would break down for the Higgs field. And you also have the so-called magnetic modes, so the spatial modes of the gauge bosons, which also would fall into this category. So even if your couplings were very small, which it's certainly much smaller than it is for QCD, you would still need non-perturbative input for the phase transition. And how to do that was derived using an effective field theory approach in this series of paper in the 90s. It relies on the fact that in the Matsubara formalism, you have discrete frequencies, which are the even multiples of 2 pi t for bosons, and the odd multiples of pi t with no zero frequency mode for fermions. So all the non-zero Matsubara modes, so all the fermionic modes and the non-zero bosonic ones, then have frequencies of the order of the temperature, and they can be integrated out non-perturbatively if you really assume that you have this scale separation between the 2 pi t and the GT or G squared T modes. So that brings you to what is called the dimensionally reduced theory. Sorry. If your Euclidean domain looks like that with the compactified time dimension, once you dimensionally reduce, you completely lose this time dimension, and you are left with a three-dimensional theory, which is EQCD in the case of pure QCD. Then you have an intermediate scale, which is that of the electric modes of the gauge bosons, which have masses of order GT, and they can be integrated out either perturbatively or non-perturbatively. So what remains is an effective theory with the zero modes of the scalars and the spatial gauge bosons. So in the case of QCD, you would just have the spatial gauge bosons, and you would have what is called MQCD. So this theory is not problematic on the lattice because it's a purely bosonic three-dimensional theory, whereas if you started from the standard model, of course, you would have many problems on the lattice because you would have chiral fermions which transform under different gauge groups. So, but here fermions can be integrated out perturbatively if you also want to test whether this first perturbative step is under control. You can put on the four-dimensional lattice the gauge and the Higgs sector of the theory and see how it compares with its dimensional reduction strategy approach. So then you can eventually solve this three-dimensional theory on the lattice, and this is the state of the art for that. For the standard model at the physical point is shown here. So here you have the Higgs condensate, and you see that at a temperature of approximately 160 GeV, it changes sign without any discontinuities. So it's really a crossover. And you see also the green bands are the perturbative calculations on the symmetric and broken phase side of the transition. So you see that there is really a small window for the standard model where the perturbative calculation is breaking down and non-perturbative input is needed. And then if you combine it with the determination of all the other degrees of freedom, you then get these curves for the thermodynamics of the standard model across the phase transition. Well, not the phase transition, but the crossover transition. So you see that there's a 1% uncertainty. So we really have thermodynamics at the 1% level for the standard model at the Electroweak transition. And just a comparison with, oh, sorry, I forgot to make another point. The other point is that the ideal gas result would be approximately 35.1 in these units. So kind of like 2% below what the interacting result is. So this is very different from QCD. So these are the results for the QCD transition. So this is the pressure. You see that the lattice data shown here have even at a temperature that's approximately 5 times the pseudocritical temperature, you're still 20% below the non-interacting gas result. And you see that the perturbative calculations, which are the two bands, they can follow quite well the trend of the lattice data, but they have very large uncertainties, much differently from what is shown before. And also the trace anomaly is quite significant, whereas in this case, the difference between these curves, which is the trace anomaly, would be much smaller. Because, and the difference, of course, is that here at the Electroweak scale, all but a handful of degrees of freedom are weakly coupled, and it's just these bosonic modes which are sensitive to non-perturbative physics. And finally, of course, these are results for the standard model, but there's, of course, a very active industry in studying many beyond the standard model models, sorry, to see if they have a first order phase transition and how strong it is, and then how would be the bubble nucleation rate, and then from that, how would be the gravitational wave signal. I'm sorry, I don't have the time to go through this, but this would just to give you an idea of what are the tools and how they differ and how they're similar from what we are familiar with in the case of QCD. So with that, I can move to the second part of my talk, which is about production and interaction rates. So the general approach I think here is to think, if you have some degree of freedom which may be about to freeze out from the early universe, or if it's weakly coupled enough that it's not even in equilibrium, then you might think of this degree of freedom as being a slow mode, and you separate it from the fast modes at which you integrate out to obtain evolution equations for the slow modes. And what is fast and what is slow is, of course, determined by the standard clock, which is the Hubble rate. So then, based on this approach, you can construct a formalism for production and equilibration rates. Now, if you think about this toy Lagrangian, where you have some particle phi, which is weakly coupled with some coupling H to a thermal bath, which could be the standard model or some beyond the standard model physics at high temperature. And this bath will have its internal couplings G. And then with that, you can prove to first order in this coupling H, but to all orders in the internal couplings of the bath, that the single particle phase space distribution for the fields phi obeys this evolution equation. So it equilibrates essentially according to this equation, where the rate is given by this spectral function of this current J, which is exclusively built out of bath fields. So a few remarks is that this is a single particle phase space distribution, so it's sensible only for sufficiently weakly interacting particles, because otherwise you would need more than just a single particle distribution. You can also obtain a similar approach for conserved charges and their number densities. More remarks is that, as I've said, this derivation is based, and it also relies on this separation of timescales between the production and equilibration rates and the plasma dynamics. Now, if you think that this contribution here is negligible because it's the current phase space density is very small, then what you have here is the so-called production rate. And then this equation also gives you an all-order proof of the equivalence between the production and the equilibration rates. That was already known from just detailed balance in the leading order Boltzmann approach. So at first order also in the internal couplings of the bath. But this goes beyond that, because if a perturbative expansion is applicable, then you recover the Boltzmann approach, but it does not rely on the perturbative approach. And also it makes higher order more natural in this approach. And it's also easier to include non-perturbative input in this framework if needed. I point out to Philip Chico's talk on Wednesday, where he will show something related, but to the case of QCD and heavy ions rather than cosmology, where you can put non-perturbative input into this type of rate equations. Now, there have been many applications of this thermal field theory formalism to heavy ions and to cosmology. I will only touch a few in this talk. I point out to the existence of related methods that give similar results, such as Kadanoff-Bain equations. There are also cases where the phase space density is much larger than 1. So these are clearly bosonic modes that are highly occupied, for instance, during gray heating. And then this expansion in what I call here H would not work anymore. And then you need, for instance, classical non-perturbative methods. There has been recently the release of this sort of broad purpose code called Cosmological for this matter here. Then a few final remarks is that in cosmology, of course, when you do a time derivative, you also have to account for the expansion of the universe so that your left-hand side becomes like that. And in many cases, you're not directly interested into the density, but in some of its integrals. For instance, this one gives you the number densities, and then you obtain this equation here. And if you have the scale separation between the fast and slow modes, and if the coupling is mode so that you can expand perturbatively the right-hand side, then you reproduce the standard Boltzmann results for frequencies of the order of the temperature. But again, here the quasi-particle picture was not necessary in the derivation. And to show you an example where also this fact about at some point losing the quasi-particle picture, I show you this example of thermal production of the massless state, which would be gravitational waves. So this is based on work by my collaborators and myself, and by Ringwald and collaborators. So of course, in the early universe, there are many potential sources of gravitational waves. I've discussed phase transition. There's of course inflation, there's reheating, there are cosmological defects. All of these sources are to some degree model dependent, possibly, or speculative. There's a very nice review here. On the other hand, it's of course uncontroversial that the early universe was in a phase of thermal equilibrium. And it's also uncontroversial that gravitational waves can also be produced from a thermally equilibrated medium. So even if its net quadrupole is 0, you still have fluctuations around equilibrium that can source gravitational waves. So in the formalism I've just described, now the current would be given by the stress energy tensor over the Planck mass. So as long as the temperature is below the Planck mass, this coupling is weak, and then this gravitational wave would never reach thermal equilibrium, and they would just accumulate over the thermal history of the early universe. And then, because by the previous arguments, you can find this expression for their production and equilibration rates with this spectral function of the shear stress tensor. And this rate here not only determines the production rate from the thermal medium, but it also determines how previously emitted gravitational waves could be absorbed by the thermal universe. So I have this quantity, and if I wanted to compute it perturbatively for energies of the gravitational wave of the order of the temperature, I can look at the spectral function. What the spectral function means is that you have to take this two-point function and take its cuts. So if I take the leading order diagram, I just have one cut. And that corresponds to taking the square of this matrix element and convoluting it over the statistical function of the cut states and with on-shell kinematics, which makes it zero because you can't produce on-shell states from on-shell massless state from other states. So that would be kinematically forbidden, and you need extra scatterings to have a non-zero production rate. So the complete leading order calculation requires not one loop, but two loops for this spectral function. And that corresponds to considering, once you take the cuts, all 2-to-2 scatterings between standard model particles yielding a graviton. So those would be the diagrams for the spectral function, and those would be sum of their cuts. So you see there's always a graviton in the final states, which emerges from some 2-to-2 scatterings between standard model particles. And so eventually then you get this result, which looks like a Boltzmann equation for the production rate, because you have a phase space integration, matrix element squared, and thermal distribution for the thermal scatters. Indeed, it looks a lot like a Boltzmann approach, as I said before, but still having it formalized in terms of thermal field theory also make it clearer how to address one issue that emerges from this integral. That is that when you integrate over the entire phase space, you would naively get infinite, because you would run into the very efficient Coulomb scattering in the infrared, so this gauge boson mediated scattering, which would naively diverge, because what's happening is that you're becoming sensitive over the collective physics of the early universe plasma, in particular those that happen at the scale GT, which are screening, Landau damping, and plasma oscillation. And that can be addressed by performing what is called Hartmann loop resummation. And once you do that, you obtain finally a production rate which is finite and which has this logarithmic enhancement from the ratio of the two scales. So these are the results we obtained for the production rate. And you see that once you scale the leading temperature dependence, the only effect you have is running coupling, which makes it decrease on modulo this large temperature dependence as a function of temperature. And our calculation is valid for energy and momenta of the order of the temperature for the produced gravitational wave. We can extrapolate down to zero, and this extrapolation is well behaved in the sense that, contrary to previous determination of similar rates, that there are no unphysical large negative dips. But in any case, the fact that it's better behaved does not mean that it's correct, the calculation that is happening here, because this is where I come back to what I was saying before about the fact that at some point the quasi-particle picture stops making sense. So we started with this situation where we're producing a gravitational wave with energy and moment of the order of the temperature. So that means that you have well-defined vacuum-like quasi-particle external states, at most Hartmann loops internally. If I make my radiated graviton a bit softer, what's happening is that this intermediate state becomes a bit longer lived. This angle becomes a bit smaller, and I need to worry about collinear kinematics, soft kinematics. I may have to consider Hartmann loop quasi-particles for the initial and final states. And if I make it even softer, at some point, this intermediate state would be so long-lived that its lifetime would overlap with the mean free time between these processes that happen all the time in an equilibrated medium. So that means that the scattering picture would completely break down because the gravitational wave can no longer resolve the microscopic scale of the plasma constituents. And nothing I'm saying here is really specific to gravitational waves. It's just the handle I'm using to keep this anchored in physics, but it's there for any type of thermal production calculation. In the case of gravitational waves, what would happen is that in this very infrared regime of long wavelengths, the gravitational wave is now produced from hydrodynamic fluctuations. So if you have a shear flow gradient because of a fluctuation around equilibrium, that would source gravitational wave production in the direction transverse to this gradient. And then you can show that the rate at which this happens is proportional to the shear viscosity of the plasma. And now here I have to proceed a bit fast. The shear viscosity itself is what damps also these gradients in hydrodynamics. And in general, it's dominated by the slowest processes in thermal equilibrium. So for instance, for the standard model in the symmetric phase, these are those that only involve right-handed leptons. So that's why you have this inverse proportionality to the hypercharge gauge coupling, which gives this first estimate for the shear viscosity. So then if you put these rates on this plot, so here it's the contribution from scattering and here it's the contribution from hydrodynamics, you see that the contribution from scattering peaks at the frequency that it's a few times the temperature, and that would redshift at decoupling, so at the time the cosmic microwave background was released, to a temperature that's still at the order of the decoupling temperature. So that means that this peak here is today to be found in the same range where you find the peak of the CMB, which is the microwave range. And the amplitude of the peak is linearly determined by the highest temperature that was ever reached in the early universe. And then on the other side, you have instead the hydro tail in the infrared, and there is no clear recipe on how to connect the two. That is an open issue in thermal field theory in production calculation for any type of production rate. So just to finish this with the cosmological implications of what I just told you. So the direct detection of this gravitational wave production mechanism is challenging in the medium term because detectors in this very high frequency regime are now being thought of, but there is nothing yet that is being constructed. And in any case, it's not clear what the sensitivity would be. But there's an indirect constraint that you can put because the area under this curve gives you the evolution rate of the total energy that the universe would store in gravitational waves over its evolution. And if you store energy in gravitational waves, you're storing more energy in radiation. And the amount of energy that has been stored in radiation is constrained by measurements that you can extract from the CMB and from Big Bang nucleosynthesis, because both are sensitive to how much energy was stored in radiation at the time they were produced. And for reasons that are related to neutrinos, this is called the NF. So if you require that the amount of energy that is stored in gravitational wave corresponds to the current theoretical uncertainty of the standard model predictions for this quantity, so just from neutrino physics, then you can obtain an upper bound on the temperature that was ever reached in the early universe, which you obtain this number for the standard model universe. You obtain a number twice as large if you consider the MSSM, as these authors have done, because the extra gravitational wave production that happens in the MSSM is more than compensated by the extra dilution that happens when the supersymmetric degrees of freedom decay into standard model degrees of freedom. Finally, if I have a few minutes left, I will finish by moving to massive particle production. So now I've shown you how thermal field theory rates can be defined and computed for the production of a massless state, gravitational waves. Now I will move to massive states. Now I will put this in the frame of a model, which I don't really want to sell to you. I mean, it's an economical extension of the standard model where you just add right-handed neutrinos. And with that, you can address neutrino masses and baryon asymmetry with what is called leptogenesis. And you may also have specific realization where you can produce also dark matter candidate. Now, whatever you may think of this model, the main point I want to make here is that as in many BSM models, the parameter space can be pretty broad. So you see here that there are realizations which have very heavy right-handed neutrinos and other that are more testable, where these right-handed neutrinos are about the electroweak scale. But whatever realization you pick, for instance, assume the mass would be around here, you still have to follow the physics of this model from very high temperature down to low temperatures. So you need to know the rates to be able to compute the rates from the ultra-relativistic regime down to the non-relativistic regime. And that is a common feature of many models once you have explicit mass scales and the need to compute rates. So for instance, in this model, this was done. This is for a particular choice of masses for these right-handed neutrinos and for the Yukawa couplings. The rate is given by the spectral function of the operator that couples to the right-handed neutrino, so this standard model operator. And you see here that there's quite a bit of rich physics because you have above the electroweak crossover, you are well below the Hubble rate in terms of your rates. Then you would have a period where the rates much exceed the Hubble rate. So these states would enter thermal equilibrium, then they would leave thermal equilibrium again, then they would decay, and their decay would become fast again at some point. So you need to be able to compute the rates over 8 or 9 orders of magnitude in temperature using techniques that can change dramatically as you cross different regimes and also different phases of the standard model. And all that has been done over the past decade or so, and you can find a nice, very recent review in here, where lessons here can also be applied to all sorts of other models. And so let me show you what happens in the ultra-relativistic regime. So you might say that here in the first approximation, the mass is negligible. And then you would say, well, I just have my elastic 2-to-2 processes. Possibly I might need to worry about thermal loop resummation for some of these diagrams. So it's definitely true that you have these 2-to-2 processes, but that wouldn't be the whole story. Because you may also have that this process might be allowed or might not be allowed, depending on how the three masses relate to each other. But given that the masses are much smaller than the temperature, you also have to consistently incorporate thermal masses. And given that masses are much smaller than the temperatures, this process would, in any case, be very collinear, which means that it will have a long duration, a long formation time, so that during the long duration of this process, soft gauge boson scatterings with the other constituents of the medium can happen and can happen multiple times. And then you have to account for their interference in what is called the Landau-Pomeranchuk-Migdal effect, which is to be addressed by some form of ladder resummation. This is an area where there's been an exchange of techniques from hot QCD, because in the case of hot QCD, this was dealt with in the 90s in the context of jet modifications as they traverse a quark-gluon plasma. And that was done in this series of papers. So this wouldn't happen in what I've shown before for gravitational wave production because of the details of how the graviton couples to the standard model. And this is also very important beyond sterile neutrinos. For instance, the fact that you have these effective 1-to-2 processes can be very important for thermalization during reheating because these processes are number non-conserving, so they can be very efficient for chemical equilibration. And they are also efficient for energy equilibration. So there's quite some literature on the subject here. And there's also a very large body of literature on the subject of thermalization in QCD, where these processes also play a very important role. Finally, they can also play an important role if you want to study the equilibration. Yes?
5 minutes left.
Okay, thank you very much. They're also very important if you want to study the equilibration of the Yukawa interactions of the right-handed electrons, which are those that have the smallest Yukawa couplings in the standard model. And then you want to know when the Yukawa interactions are or are not in thermal equilibrium. And if you look at the effect this has, so this is a plot of this LPM resummed rate. So this is the ultrarelativistic regime as it approaches the relativistic regime. So the red is the full LPM resummed, and the dotted lines are the tree level. So you see that here in the relativistic regime, the tree level does a very good job, but here the tree level misses the resummed answer by a factor of a few. Now, if we move to this relativistic regime, there, as we saw, the tree-level result seems to be doing a good job, but still it receives next to leading order corrections that are now available. So these next to leading order corrections are both in the form of real processes, such as these 2 to 2 or 1 to 3 processes, but also of virtual thermal corrections, so that this is a thermal loop in here, not just a vacuum loop, which would be known already since many decades. And these real corrections are infrared divergent if you have gauge bosons, which are massless. And these thermal virtual corrections are also infrared divergent, and only their sum is physical and infrared finite. And this is a very important point in particular because there exist tools like generators that use some form of automation to compute real processes. And if you use them for some model where you have a leading order contribution and you add to it its next to leading order real corrections, if there is this sensitivity to infrared physics, you might be then doing something scheme dependent, which might significantly overestimate the rate, because these type of processes are not directly included in this type of generators. Je suis dans une vision. So these processes would not be included in generators. But now there has been brought forward an efficient algorithm for their evaluation, which might eventually lead to the possibility of automating them as well. So here finally is the result where you can merge all that is known about these rates. This is for the symmetric phase, sorry, I forgot to say. So you have here the ultra-relativistic regime, which approaches the relativistic regime and goes down into the non-relativistic regime, where it agrees with results that were obtained using OPE or EFT calculation deep into the non-relativistic regime. And with that, I can come to my conclusions. So I've shown you a bit of the thermal field theory formalism for thermodynamics and phase transition, which is extremely well tested for the standard model. And it's being applied to models of physics beyond the standard model with an outlook on first order phase transition and gravitational wave production. I've then discussed the formalism for thermal production and interaction rate, which, even though it does not require quasi-particle, it does reproduce quasi-particle-based Boltzmann results where they apply, and it also shows how it's easier to obtain regions of phase space where the Boltzmann result would not apply, such as the hydrodynamics contribution to the thermal gravitational wave production, which I've discussed, and it's a contribution to the gravitational wave spectrum, which is guaranteed to be there, and that contributes to NF, and the methods used I've shown are applicable to any massless state that's coupled to the plasma. And then I've shown also how you deal with massive states, where the fact that you have broad parameter spaces and also a potentially very large thermal history of the early universe make it so that you may need to know these rates from temperatures that are much above the masses to temperatures that are well below the masses. And there has been progress in that with also interdisciplinary connection to hot QCD and the availability of next to leading order results. And with that, that was my slide. Thank you very much.
Yeah, thank you very much, Jacopo, for this very nice overview. Question, comments, first here in the audience, but also, okay, I have to look if there's something in the chat. So while I'm, okay, yeah, wait a second.
So concerning gravity waves, do I understand correctly that this infrared TEO is not very important for the density, energy density?
Well, it's not clear because essentially it's a matter of cutoffs. So let me.
But in the plot that you showed with the power law, okay,
so this
one
is right. So this plot here is in the log units have been chosen as such that the area is really what determines the rate without any other. Well, there is a direct proportionality factor, but it's really the area. So you see that.
So from the point of view of an effective,
yeah. If you extrapolate this down here, oops, or if you extrapolate this up here, you see that there is quite a significant.
No, I understand, but look at how many orders of magnitude you have on the y-axis. So I think if I do the naive computation, I do how much is the difference from the point of view of energy density?
So when we did the first work here, we took two simple ansatz. So I think for one, we integrated up to here, and from the other one, we took this one down here. And it turned out that this was even higher, could be even higher than the 2221, if this cutoff moved to about 1 or so. So if you cut it off here, then I agree with you that it's much smaller. But
no, I'm just wondering if it's really from the point of view of an effective. Yes. How much the difference really is, because for number density, I understand that it could be vastly different, but for energy density,
so this is already what is in this plot is already for energy density. It's really for energy density. So even if there is an extra power of K, which further suppresses the infrared, it's still surprisingly sensitive to the infrared.
So how much do you think it can be the difference? 10% or 100%?
From hydro alone, probably more 10% than 100%. But eventually, I don't know when, but if at some point the methods for dealing with all the intermediate region is figured out, then I wouldn't be surprised if it's order 1.
Okay.
So not just hydro, but what is missing to get a single curve.
Okay. Also a small comment concerning the reheating temperature.
Yes.
The bound that you get here, as you probably know, is much weaker than the one that you get from inflation. So it's a bit unphysical point.
Yes, at the moment it's not stringent. I agree. It's one or two orders of magnitude above the one from vanilla inflation. Yes.
Okay, thank you.
Okay, if there's no further questions, so in the Zoom chat, please raise your hand. I mean, virtually, if you want to ask something. I have one last one because we also have to go on. If I look at your results on hard thermal loop you presented, I'm always surprised by the staggering error bars, because in this higher resummation
for the thermodynamics, are you?
Yes. In the higher orders of your of hard thermal loop, you have resummed vertices and resummed propagators. Why is the error bar so big? For me, it looks like an overestimation of error bars. Yes. This is amazing. I mean,
good question. Yes,
for me, it always looks as if you overestimate your error bars.
Right. So these are not my calculations, so I'm not super familiar with them. I think the error bars comes mostly from renormalization scale variation. And why that is still so large, given that this is a 3-loop calculation, that's a good question. And I don't have an equally good answer.
Okay, yeah. In my opinion, but that's of course from outside, it looks like as if the error on the coupling, it's essentially the strong coupling which gives you the error is overestimated. But okay, I mean, that's just a comment from the side. So we have to go on because we are already 5 minutes in the coffee break and we need the coffee. So let's thank Jacobo again.